Friction deals with relationships between two external forces, weight and the force applied to move an object, and the two reaction forces, the normal reaction force and the friction force. In video 2 of this series, we saw that if an object to be moved is on a horizontal surface and the sliding force is applied parallel to the surface, then the weight of the object is the only force pushing the surfaces together, so the normal reaction force Rn equals the weight of the object W. When the applied force Fa is parallel to the surface, all the applied force is used to slide the object, and therefore the applied force equals the reaction force. So, for friction on a horizontal surface, when the applied force is parallel to the surface, we can say the weight of the object equals the normal reaction force, W equals Rn, and the applied force equals the friction force, or Fa equals Ff. So when using the general friction formula, friction force maximum equals the coefficient of friction times the normal reaction force, we can substitute Fa for friction force maximum and the weight for the normal reaction force, so our formula then becomes the applied force Fa equals the coefficient of friction times the weight of the object. Consider an object where a force is applied up or down at an angle to slide an object across a surface. Because our applied force Fa is a vector, it can be separated into a horizontal component, Fax, and a vertical component, Fay. Because Fa, Fax, and Fay are sides of a right-angled triangle, and if sigma is the angle of inclination of the force, then Fax is the cosine of the angle of inclination times Fa, and Fay equals the sine of the angle of inclination times Fa. So here we have a force applied at an upwards angle to slide an object along a horizontal plane. As we can see here, our angle of inclination, our applied force upwards at an angle, so we can break that applied force into a vertical component, Fay, and we can find Fay from the sine of our angle of inclination. Fay will equal the sine of the angle times the applied force. The horizontal component, Fax, we can find from the cosine. Fax equals the cosine of the angle times the applied force. Here we have a sliding force applied downwards at an angle. In this case, we have the same angle of inclination. We can still break the applied force into a vertical and horizontal component. The vertical component, Fay, will be the sine of the angle of inclination times the applied force. So Fay will equal the sine of the angle of inclination times Fa, and the side adjacent, or the horizontal component, Fax, will equal the cosine of the angle of inclination times the applied force. Example 1. A force of 250 newtons is applied upwards at an angle of 25 degrees to the horizontal to slide a crate across the floor. What are the horizontal and vertical components of the sliding force? So example 1. A force of 250 newtons is applied upwards at an angle of 25 degrees to the horizontal to slide a crate across a floor. What are the horizontal and vertical components of the sliding force? Step 1. Draw the system. So we draw the system showing the applied force, the angle of inclination upwards of 25 degrees, and the vertical component FAY and the horizontal component FAX. Step 2. Find the vertical component of the applied force. Sine of 25 degrees equals the side opposite FAY over the hypotenuse FA. So if we cross multiply, FAY equals the sine of 25 degrees times FA. FAY equals 0.423 times 250 newtons. FAY, or the vertical component of the applied force, is 105.75 newtons. Step 3. Find the horizontal component of the applied force. Cosine of the angle of inclination equals the side adjacent FAX over the hypotenuse, the applied force FA. Cross multiplying, FAX equals the cosine of 25 degrees times FA. FAX equals 0.906 times 250 newtons. FAX equals 226.6 newtons. Example 2. A force of 250 newtons is applied downward at an angle of 25 degrees to the horizontal to slide a crate across a floor. What are the horizontal and vertical components of the sliding force? As you'll notice, the force and the angle of inclination are the same as example 1, but in this case we are pushing down on the object, not pulling up. Example 2. A force of 250 newtons is applied downwards at an angle of 25 degrees to the horizontal to slide a crate across the floor. What are the horizontal and vertical components of the sliding force? Step 1. Draw the system. So we have 250 newtons at an angle of 25 degrees to the horizontal. We have our vertical component down, FAY, and our horizontal component, FAX. Step 2. Find the vertical component of the applied force. Sine of 25 degrees equals FAY divided by FA. So FAY equals the sine of 25 degrees times FA. FAY is 0.423 times 250 newtons. FAY is 105.75 newtons. Step 3. Find the horizontal component of the applied force. Cosine of 25 degrees equals FAX divided by FA. FAX equals cosine of 25 degrees times FA. FAX equals 0.906 times 250 newtons. FAX equals 226.6 newtons. It should be noted for examples 1 and 2, the applied force and the angle of inclination are the same. Therefore, the magnitude of the horizontal and vertical components of the applied force have the same magnitude. It doesn't matter if the applied force is up or down. However, the vertical component, FAY, will be opposite in direction for a force applied upwards compared to down. If the applied force is upwards at an angle, the vertical component is up. If the applied force is down at an angle, the vertical component is down. When you pull up or push down at an angle on an object on a horizontal surface, the component of the force that is parallel to the surface, FAX, is the portion of the applied force that is trying to slide the object. So FAX is the force that produces the reaction friction force, FF. So the friction force will equal the horizontal component of the applied force whether we are pulling up or pushing down at an angle to the horizontal. So the friction force Ff will equal the horizontal component of the applied force Fax. So here we are pulling up on an angle on an object on the horizontal surface. We can see the horizontal component of that force Fax, and the friction force will equal the horizontal component Fax. If we are pushing down at an angle to the horizontal with an applied force, again, the horizontal component of our applied force will equal the friction force in magnitude. When we apply a sliding force at an angle to an object, we can either pull up or push down at the angle to the horizontal. Whether we pull up or push down on the object will determine the magnitude of the force pushing the object into the surface, and therefore the value of the normal reaction force Rn. That is, the value of Rn will be different for a force applied at an upwards angle compared to an identical force applied down at the same angle. For the shown object, since it is not moving in a vertical direction, then forces up equal forces down. Forces up are the normal reaction force, Rn, and the lifting portion of the applied force, Fay. Forces down are the object's weight, W. So we can say Rn plus Fay equals W. And if we want to transpose for Rn, we can say Rn, the normal reaction force, equals the weight of the object W minus the vertical component of the applied force Fay. So if we lift upward at an angle to pull an object, then the friction force Ff equals the horizontal component of the applied force, which is Fax, and the normal reaction force Rn equals the weight of the object minus the vertical component of the applied force. Example 3. 100 kilogram mass sits on a horizontal surface. What is the normal reaction force if an upwards force of 100 newtons is applied at 20-degree angle to the horizontal? So we have a 100 kilogram mass sitting on a horizontal surface. We have an applied force of 100 newtons upwards at an angle of 20 degrees, and we want to know what the normal reaction force is. Step 1, finding the weight of the object. Weight equals mass times g. Weight is 100 kilograms times 9.81 meters per second squared. The weight of the object is 981 newtons. Step 2, finding the vertical component Fay of the applied force. Fay equals the sine of 20 degrees times Fa. So Fay equals 0.342 times 100 newtons. Fay equals 34.2 newtons. Step 3, finding the normal reaction force. Forces up equal forces down. Forces up are Rn plus Fay. A force down is the weight of the object. Rearranging the equation, transposing for Rn. Rn, the normal reaction force, will equal the weight of the object minus the vertical component of the applied force. Rn equals 981 newtons minus 34.2 newtons, so Rn equals 946.8 newtons. Our general friction formula states the maximum friction force equals the coefficient of friction times the normal reaction force. But if our applied force is upwards at an angle, then the maximum friction force equals the horizontal component of the applied force, and the normal reaction force equals the weight of the object minus the vertical component of the applied force. So we can substitute for the friction force and the normal reaction force, and our formula becomes Fax, the horizontal component of the applied force, equals the coefficient of friction times the weight of the object minus the vertical component of the applied force. So when we pull upwards at an angle to slide an object, then the maximum friction force equals the coefficient of friction times the normal reaction force, or the horizontal component of the applied force equals the coefficient of friction times the weight of the object minus the vertical component of the applied force. Example 4. A crate is pulled along a horizontal surface at a constant velocity by a rope inclined at an angle of 30 degrees in an upwards direction to the plane. If the applied force is 150 newtons and the mass of the crate is 125 kilograms, what is the coefficient of kinetic friction? So here we have our crate sitting on a horizontal surface. Applied force is 150 newtons at an upward angle of 30 degrees to the horizontal. And the mass of the object is 125 kilograms. It's moving at constant velocity, so we want to know the coefficient of kinetic friction. Step 1, finding the weight of the object. Weight is mass times g. So weight works out to 1,226.25 newtons. Step 2. Finding the horizontal and vertical components of the applied force, Fax and Fay. Fax equals the cosine of 30 degrees times Fa. Fax works out to 129.9 newtons. Fay equals the sine of 30 degrees times Fa. Fay equals 75 newtons. Step 3. Finding the maximum kinetic friction force. Since the object is moving at constant velocity, then we know the maximum kinetic friction force equals the horizontal component of the applied force. So the maximum kinetic friction force equals 129.9 newtons. Step 4. Finding the normal reaction force. Forces up equal forces down. Rn plus Fay equals W. Rn equals W minus Fay. Rn equals 1,226.25 newtons minus 75 newtons. Rn is 1,151.25 newtons. Step 5. Finding the kinetic coefficient of friction. Since we are dealing with the general friction formula, U equals maximum friction force divided by Rn, but in this case it's kinetic friction, so we're looking for the kinetic coefficient of friction UK, and it equals the kinetic maximum friction force divided by Rn. So UK will equal 129.5 newtons divided by 1151.25 newtons. So the kinetic coefficient of friction works out to 0.113